Here we are formally introducing this concept of uniform motion. Uniform here means constant, and we're talking about motion with constant velocity. So if you were to draw a motion diagram for an object in uniform motion, it would look like this. You'd have evenly spaced points, meaning that the particle is moving equal distances in the same amount of time, or you can notice that the velocity vectors, the average velocity vectors between each data point are the same length, and thus we have the same speed. If we're talking about uniform motion, we have the velocity is constant, and the velocity is still the change in x over change in time. So this is the displacement in the x direction, assuming we're moving horizontally, over the change in time. Since this is also our rise over run on a position versus time graph, then the velocity is going to be the slope of that curve. And since we're assuming that the velocity is constant, we should have a constant slope, which means that we should have a straight line as a position versus time graph for uniform motion. To reiterate, for uniform motion, we have a constant velocity, and the velocity is also the delta x over delta t, which is the slope of our position versus time graph. So if the velocity is the slope of that graph, then that means that faster speeds correspond with steeper slopes. Slower speeds are flatter lines, are closer to being horizontal. If we have a negative slope would mean that the curve is tilted downwards. That simply means that we have a negative velocity in that case, and we would have leftward motion if we're talking about a horizontal axis, or perhaps downwards motion if we had a vertical axis. The thing to remember here is this is the rise over run, so it is the rise is the vertical distance here, the run is the horizontal distance. It's not the ratio of coordinates. It's not x per t or x final per t final, but it's the difference between these x coordinates divided by the difference between the t coordinates there. And we're talking about velocity here being constant. Velocity is a vector quantity. We can let velocity be positive or negative to indicate the direction along our axis. When we talk about speed, speed is the absolute value of the velocity. So it's just the amount, ignoring or leaving off the plus or minus that you'd have with a velocity term. We'll typically use the x-axis as our arbitrary one-dimensional axis, but you could also have a vertical axis that you may call a y-axis. We'll see later how circular motion could be represented by an angle. But what we're learning here for uniform motion in one dimension could be true for any of these axes, depending on how you want to set up your coordinate system. What we can look at here is we can come back to the definition of our velocity. Again, our assumption is that the velocity is constant. And to explore this a little more, what we can do is solve for delta x by multiplying both sides by delta t. Furthermore, we can take delta x and split that apart because the displacement we know is the difference between the final position and the initial position. You can see here that we can move delta x over to the side, and we have one equation here that represents the position of a particle that's undergoing uniform motion. Where the particle is at the end of an interval of uniform motion depends on where the particle was at the beginning, plus how fast the particle is going, what its velocity is, and how long the particle is undergoing uniform motion. We can also turn this into a position function, a position function of time, by simply allowing the final position, leaving the final time to be some general t that we don't have to say specifically when it is, and then the final position is going to depend on what that final position of time is. So in practice, what this would mean would be our final position becomes our function of t. Our initial position is a fixed value because we must have started someplace, and wherever we started, that's a fixed place in the past. And in this situation, what I've done is I've broken up delta t into t minus t initial. So t would be some arbitrary final time minus t initial. This would be our starting point in time and our starting point in space. We'd need to know when we are at some location, and then we could use this equation to figure out where we would be at any future or indeed any past point in time. So to recap, an object in uniform motion would have a motion diagram that would look like this. Its acceleration vectors would all be zero because it is not accelerating, it's moving at a constant speed. The velocity graph of this particle would be a horizontal line. This is a constant value because the speed is a constant value here, constant velocity. And then the velocity is the rise over run. That's the slope of the position versus time graph. And so a constant velocity would give us a constant slope, a straight line in our position versus time graph. We can rearrange this definition of velocity and find the position of the particle at some point later on as it undergoes uniform motion, or we can turn this into a function of time if we so choose. All of this is true only for the case of constant velocity. If the velocity changes, these equations, these graphs, etc., are no longer valid. Although our understanding of uniform motion is limited to when we have constant velocity, it's possible to take a situation, a position graph of a particle that definitely has different slopes and different velocities, and we can break these up into various intervals and say that we have an interval of uniform motion here, where we have a constant slope, another interval of uniform motion, and another interval of uniform motion. Similarly, if we look at the velocity graph, we could break this up into different intervals, and we could treat each interval separately and do our calculations in a piecewise manner.